So we talked about yesterday limits, finding limits. When we're finding limits, the first thing we always do is plug it in. Plug in the value, see what we get. All right. If we get something that's a indeterminate form, we can use L'Hopital's rule. Okay. Indeterminate form is one of these guys here. Okay. 0 over 0 or infinity over infinity. All right. And then we stopped at number 7, I believe. 7 was the last one. Okay, so let's look at number 8. I want you to give number 8 a shot. Do number 8. If you haven't already, do number 8 and we'll talk about it. This one's actually a problem we've done before. We did like in August. It's the exact same problem we did in August. Let's see if you can remember how to do it. As a little review, it's good to review a little bit. Okay, so this is essentially what the question is saying. If I plug in the biggest number you can think of, what's going to happen? What? Well, what's going to happen if I plug in the biggest number you can think of times the biggest number you can think of times the biggest number you can think of times the biggest number you can think of? That's a huge number. What's going to happen? What do we use for this problem? Which some of you were doing. What do we use for this problem? Which I could tell some of you guys were doing. The paper some of you guys are looking at. Yep. Mm-hmm. Exactly, right? There's 3 categories. Anytime a limit approaches infinity or negative infinity, we have 3 categories, right? That's where I would stick to. These guys right here, right? 3 categories. Top heavy, bottom heavy, equally balanced. Okay. So my question is, which one does this fit into? What type of function do we have on top? A log, right? It's a log. We have a log on top. Okay, log function. On bottom, what type of function do we have? So it does have a square root, but what type of function are square roots? They are not exponential. No. Well, all of those quadratics, square roots, they all fall under polynomials. Okay. So we have a log over a polynomial. My question is, which one is going to get bigger faster? You can't use a calculator on this, but I like to use calculator sometimes when I'm doing these, just to remind myself. Pick the biggest number you can think of. I'm just going to use a regular scientific calculator. The biggest number you can think of. I'm going to take the natural log of it. Biggest number you can think of. Look at that number. Don't look at them, look at the number. What's happening? It's increasing. When I say the number, I mean the answer. Let me try it again. Let's see, limit. Oops, not. Let's see. What's happening? Increasing. What else? What else do you know? Definitely increasing. What else do we notice? Is there any other word you can think of besides increasing? Or any adjective you can use with adverb you can use with increase? I would say the opposite of exponentially. What does exponentially increasing mean? Exponentially increasing means this. That number is getting bigger really fast, right? That's exponentially getting bigger, okay? That's an example of exponentially getting bigger. Let me show you again what we just saw. Again, you're focused on that guy. That's the guy you're focused on, okay? Keep your eye on that guy. Mhm. Even better than that, besides steadily increasing. Yeah, it's not increasing very fast. From 43, I'm going to add another zero. If I add another zero, that goes from, look at that number. Look at that number. That's numbers, let's see, thousands, millions, billions, trillions. I don't even know what it is. It's so big that that's all the money in the world. That's all the money anyone in the world put together. Everybody. And the natural log of that's only 43. Let me put another zero to it. It went up. Not even 3. I mean, this thing is so increasing so slowly. And that's what natural logs do. They increase very slowly and they taper off and they don't increase. So as the number gets bigger, it actually won't increase as much. Okay? Now let's take a square root. Take the square root of the biggest number you realize. So again, look here. Compare. Is it increasing? Yes, right? A lot faster, right? So which one is going to get bigger a lot faster, the top or the bottom? Okay, so if the bottom increases faster, think of a fraction. If the bottom increases faster than the top at a lot faster rate, if I put the biggest number you can think of times the biggest number you can think of, what is the bottom going to be? What is overall, what's the fraction going to equal? 0. 0. And those of you that have your sheet out, thank you for pulling out your notes. That's what they're there for. Some of you, I think, hope to remember it and you don't remember it. But at the top of that is a little growth rate sheet. A little growth rate sheet. Okay? You could just use the growth rate sheet. Which grows fastest? Well, polynomials is just above logarithms. So you didn't even have to do that little experiment. You just know that polynomials grow faster than logarithms. The only thing that grows slower than logarithms are sine and cosine, because they don't grow at all. They grow and die, grow and die, grow and die, because they're just waves. They oscillate. Right? And then constants are just horizontal lines. Okay? In this class, we don't deal with factorials, so you don't have to worry about factorials. The biggest thing that grows the fastest is exponentials. Exponentials are where x is the exponent. Okay? Polynomials are anything to a power. X to the 1/2 power, x to the 3rd power, x to the 10th power. Logs are logs, or natural logs. Sine and cosine are trig. Okay, trig functions. Okay? So just by using this little growth rate sheet, okay? When I give you notes, it's not just for today, it's for in the future, especially when we start reviewing for the final. Especially when we start reviewing for the final, because when we review for the final, I'm going to give you a sheet, and it's going to have questions from August, September, October, November. Okay, so having those handy, having those, like on mine, I know mine's digital, but just having them, if you can find them, right? If you can find them within a few 30 seconds or so in your notebook, that's good. You're organized. If you can't, you got to find a better way. Okay, find a better way to be organized so you can have those handy. All right, because these questions are gimmies. They're easy questions if you know what you're looking for. If you're not, you could spend 30 minutes on this one question and still not get it right. Okay? So these are the types of questions where they're gimme questions. You got to be able to get them. Oh, okay. The top is a log, that's going to grow really, really, really slow. The bottom is a polynomial, that's going to grow really, really fast. So the bottom is going to get bigger, a lot bigger, faster. So that means if a fraction is big on the bottom, it's 0. It's bottom heavy, right? It's bottom heavy. Bottom heavy, your answer is always going to be 0. Okay? All right, so how about this guy here? Try this guy. Okay, so if you're not in a place, this one's a little tricky, especially with negatives. You have to deal with the negative. It's a big number, but it's a negative big number. Biggest number you can think of, but negative. Okay? Or even bigger than the biggest number you can think of. Normally, if this was like this, if this question was like this was positive and that was positive, I would say bottom heavy because the bottom is exponential. 0, your answer is 0, move on. But because of these two tweaks, we have to look at it a little differently. Okay? So what I usually do is I'll plug it in like I did. Negative infinity is just a negative number. If I square a negative number, I'm going to get an even bigger number that's positive. Okay, don't do this. Infinity squared. There's no such thing as infinity squared. Infinity is not a number. It's an idea. Okay, so we can't add infinity. We can't divide infinity. We can't square infinity, right? So I'm just putting a really big number. Okay, in fact, let me not use infinity anymore. Let me say really big number. Okay, on bottom, when I plug that in, what's going to happen to the power? It's going to have the same number, right? Really big number. Which one's going to grow faster, the top or the bottom? The really big number or e to the really big number? Which one is higher on the list? Exponentials. And the bottom is an exponential. So the bottom is going to grow really fast, faster. You get 0. Okay. All right. Okay. I want you to do number 10. Number 10 is the last one. You got one more and that's it. Number 10 and we're done. I'll let you work on your assignment. Number 10 is going back to finite numbers. Limit as x approaches 0. Okay, so do that one and we'll be done with this one. Okay, so I plugged in 0 over 0. I plugged in 0 for x everywhere and I got 0 over 0 the first time. So I gotta find the derivative. So the top, the numerator's got 3 terms. It's got 3 terms. So I had to find the derivative of each term. I highlighted them in green, purple, and orange. Okay, the purple term doesn't have a derivative, it's 0. So I didn't find derivative of that. But I found derivative of the green and the orange. Okay, so now I got to plug in 0 again. See what I get. So I get 1/2, 1 plus 0 to the negative 1/2 minus 1/2 over 2 times 0. Okay, so 1/2 times 1 to the negative 1/2 minus 1/2 over 0. I already know I'm going to get 0 on the bottom. So if I get something on top, I'm done. If I get 0 on the top, I got to do it one more time. Exponents first. What is 1 to the negative 1/2?
It means you flip 1 and take the square root of it. Well, if I flip 1, it's still 1. Take the square root, it's still 1. Okay? Times 1/2 is 1/2. Minus 1/2 is 0. So I get 0 over 0. Okay? So now I'm going to take the second derivative. So now I have two terms. I have this guy here, and I have this guy here on top. The bottom is just going to be 2. Bottom derivative is just going to be 2, because it only has one term on bottom. And the orange, the second one, is 0, because the derivative of negative 1/2 is 0. So really, I just got to find the derivative of the green. Okay? Well, I'm going to use chain rule. I'm going to move the negative 1/2 to the front, multiply it to make negative 1/4. Inside stays the same. Power loses 1 whole. And then I multiply by what's derivative of the inside, which is just 1. Okay. Plug in 0 now. Okay. So I get negative 1/4 times 1 to the negative 3/2 over 2. How do I do 1 to the negative 3/2? So the negative means flip 1, reciprocal of 1. Okay, the reciprocal of 1 is just going to be 1. Okay. The number on top means power. So cube 1. The number on bottom means root. Square root 1. Well, if I cube 1, I still get 1. If I take square root of 1, I still get 1. So really, it's just negative 1/4 times 1. Negative 1/4, if I divide that into two pieces, we get negative 1/8. Negative 1/8 plus negative 1/8 makes negative 1/4. When you divide something by 2, you're just cutting it in half. If I had 1/4 of a pizza and I cut it in half, I would have 1/8 of a pizza. Okay? All right. Okay, so what I want you to do now is work on those problems. Everyone has the same problems. I did this on purpose. I didn't want to do it on Delta Math because you have different problems. So if you have a question, you have resources. Your notes, obviously. You can people around you because they have the same problem, or me. Okay, so if I do a problem, I can help everybody. Okay, so I want you to work on those. The key is posted. The answer key is posted. The work's not posted, but the answer key is posted on Google Classroom. So you can check as you go. Let me double check that.